Have you ever looked up at the night sky and felt a sense of wonder? It's a vast, dark canvas, sprinkled with countless stars. Each star could be a sun to planets we haven't discovered yet. Our own galaxy, the Milky Way, is just one of billions out there. It's easy to feel small in the face of such incredible scale. But what if I told you that our entire universe, with all its galaxies, stars, and planets, might just be one among many? What if our universe isn't the only one? This isn't just a question for science fiction. It's a genuine puzzle that some of the brightest minds on our planet are trying to solve right now, today. The answer might be hiding in the most mysterious and powerful objects we know of. Black holes. That's right. Those cosmic vacuum cleaners, famous for swallowing everything that gets too close, might not just be points of no return. They could be something far more creative. They could be cosmic mothers, giving birth to brand new realities, each with its own set of rules and its own story to tell. Before we can imagine a universe emerging from a black hole, we need to understand what these enigmatic objects truly are. A black hole is what remains when a massive star, many times larger than our own sun, reaches the end of its life. The star collapses under its own immense gravity, squeezing all of its matter into an incredibly tiny space. The gravitational pull becomes so strong that nothing, not even light, can escape its grasp. Think of spacetime as a flat rubber sheet. If you place a bowling ball on it, the sheet will bend and curve. A black hole is like placing an infinitely heavy pinhead on that sheet. It creates a bottomless pit, a well in spacetime so deep that anything that falls in can never climb back out. The edge of this pit is called the event horizon. Once you're past that point, all paths lead to the center, a point of infinite density called the singularity. It is here, at the singularity, where our current laws of physics completely break down and fail us. Scientists have spent decades studying these cosmic monsters. We've detected the gravitational waves they create when they merge, and we've even managed to take a picture of a black hole's shadow. Now let's connect these two giant ideas, the mystery inside a black hole and the possibility of other universes. The theory we're exploring is called Cosmological Natural Selection, sometimes known as the theory of thickened universes. It was proposed by a brilliant physicist named Lee Smolin. He looked at the strange properties of our universe and asked a simple but profound question: why is our universe so good at making black holes? Smolin's idea is inspired by Charles Darwin's theory of natural selection here on Earth. Smolin proposed that every time a black hole forms, the singularity at its center doesn't just crush matter into a single point. What if, instead, it bounces and triggers the creation of a brand new universe, hidden from our own? In this scenario, a new universe would be born from the other side of the singularity. This new universe would inherit the fundamental laws of physics from its parent universe, but with slight random changes. Think of it like cosmic DNA. The new baby universe would be very similar to its parent, but not an exact copy. Some of the physical constants, like the strength of gravity or the mass of an electron, might be slightly different. This leads to a fascinating conclusion. Universes that have laws of physics that are good at making black holes will have more offspring. Over countless generations of universes, these types of universes would become the most common. To truly grasp the idea that a black hole could create a universe, we must first journey into the heart of one. Imagine a star far more massive than our sun. For millions of years it burns brightly, but eventually its fuel runs out. The outward push of fusion stops, and gravity takes over completely. The star's core collapses catastrophically upon itself, crushing matter into a space so small it defies imagination. The first feature you would encounter is the event horizon. This isn't a physical surface you could touch, but rather a boundary of no return. Think of it as the edge of a cosmic waterfall. Before you reach the edge, you might still have the power to turn back. But once you drift over that invisible line, your fate is sealed. All paths will inevitably lead you towards the black hole's center. If you could survive the journey past the event horizon, you would be drawn towards the singularity. Here, all the mass of the original star is thought to be crushed into a point of zero volume and infinite density. Our current understanding tells us this is what must happen. However, this idea of infinite density is a signal that our theories are incomplete. It's where Einstein's smooth universe clashes with quantum mechanics. Black holes don't just sit there silently in space, they actively shape the cosmos around them. Albert Einstein revolutionized our view by showing that space and time are woven together into a single four-dimensional fabric, spacetime. Massive objects create dips and curves in this fabric. Planets orbit the sun not because of some mysterious pulling force, but because they follow the straightest possible path through curved spacetime. Now imagine the effect of a black hole. It's not just a bowling ball on the sheet. It's a pinprick with near infinite mass. It doesn't just create a gentle dip. It punches a bottomless hole through the fabric of spacetime. The curvature is so extreme that spacetime itself is dragged along with it. This is why nothing can escape. All possible paths forward in spacetime lead only to the singularity. This extreme warping has consequences we can observe from Earth. When two massive objects spiral towards each other and merge, they create violent disturbances in spacetime, gravitational waves. These waves travel across the universe at the speed of light, and using incredibly sensitive detectors, we have finally learned to hear the sound of these cosmic collisions, confirming Einstein's predictions. While black holes can seem like science fiction, they are very real. We believe they come in several sizes. The small ones are stellar mass black holes, formed from the collapse of a single massive star. At the other end are the supermassive black holes, true monsters with masses ranging from millions to billions of times that of our Sun, found at the centers of most large galaxies. At the center of our Milky Way lies Sagittarius A, a supermassive black hole with a mass of about 4 million suns. Its immense gravity governs the orbits of nearby stars, holding the entire galaxy together. The existence of these supermassive black holes poses a major puzzle. How did they get so big? It's hard to imagine a single star massive enough to form a billion solar mass black hole directly. Our Milky Way could contain as many as 100 million stellar mass black holes. The fact that our universe is so proficient at making these objects is a deeply significant clue. It is this abundance that leads to the radical question we are exploring. Could this be the universe's primary function? Is creating black holes the key to cosmic reproduction? We move from known astrophysics into truly radical territory. Cosmological natural selection was pioneered by Lee Smolin in the 1990s. He looked at the universe not as a static stage, but as a dynamic system that could evolve. He connected Darwin's theory of evolution with black hole physics. Darwin's theory is based on reproduction with variation and selection. Those with better variation survive and reproduce more successfully. Smolin bravely asked, what if this same logic could be applied to entire universes? This is where black holes enter the story in a spectacular new role. Instead of being cosmic tombs, they become cosmic wombs. Every time a massive star collapses, something extraordinary happens at the singularity. It triggers a rebound that gives birth to a brand new baby universe, completely inaccessible from our own. This creates a vast cosmic family tree, with universes constantly reproducing through black holes. Universes good at making black holes will have more offspring. Over countless generations, these types would become most common. It's cosmic survival of the fittest, on the grandest scale imaginable. The formation of a black hole becomes an act of cosmic reproduction, ensuring the cosmic chain of creation continues. For cosmic evolution to work, it needs variation. When a new universe is born, it inherits the fundamental physical laws of its parent, but with slight, random changes. Think of the laws of physics as cosmic DNA. This DNA gets passed down, but not perfectly. Tiny mutations occur during the bounce. One universe might have slightly stronger gravity, another might have heavier electrons. Most changes would be disastrous. A universe with gravity too weak for stars would be sterile. It would never create black holes, and would have no offspring. It becomes an evolutionary dead end, its unique physical laws vanishing with it. Over countless generations, a clear trend would emerge. The universes most successful at reproducing would come to dominate the multiverse. Their physical laws would be passed down again and again. The multiverse would select for universes that are fertile, optimized for black hole production. This provides an elegant explanation for our cosmos's fine-tuning. We live in a descendant of successful universes. This makes a testable prediction. If our universe is a product of this evolutionary process, it should be at a peak of fitness. Any tweak to our constants should make black hole formation harder, not easier. This brings us to a puzzling fact about our universe. The laws of physics seem remarkably well suited for creating black holes. For stars to form, you need gravity strong enough to pull gas clouds together, but not so strong the universe recollapses. You need nuclear forces balanced just right for stars to ignite and burn stably, creating heavier elements. And you need massive stars that eventually collapse, triggering supernovas and leaving behind black holes. Our universe is incredibly good at this. Change any fundamental constant by just a small amount, and this delicate process falls apart. If the strong nuclear force were weaker, stars wouldn't ignite. If electromagnetism were different, stellar cores wouldn't be stable. For a long time, this fine-tuning has puzzled physicists. Why does our universe have these specific values? It seems like an incredible coincidence that they allow for a complex, interesting universe. Cosmological natural selection offers a direct answer that doesn't rely on luck. Our universe isn't fine-tuned by chance. It's the product of an evolutionary process, a descendant of successful parent universes. Our universe's laws aren't random. They've been honed over countless cosmic generations. We live in a universe good at making black holes because universes that weren't simply didn't reproduce as successfully. So how exactly could a black hole give birth to a new universe? The answer lies in reimagining the singularity. Einstein's general relativity predicts infinite curvature and density, a red flag for physicists. A new theory combining gravity with quantum mechanics is needed. One leading idea is that there's a fundamental limit to matter compression. Spacetime itself might be made of tiny, indivisible quantum units. If matter can't be crushed into an infinitely small point, what happens when it reaches maximum density? It bounces. This big bounce would rebound outwards, creating a new, expanding spacetime. This wouldn't happen within our universe. It would form a completely separate baby universe, forever causally disconnected from our own. From inside, its history would begin with a big bang. This solves the singularity problem, replacing infinite endpoints with dynamic creation. The energy and information falling into black holes aren't destroyed. They're recycled as building blocks for a new cosmos. The black hole acts as a cosmic furnace, taking matter from a dying star and reforging it into the seed of a new reality. This provides the engine for cosmological natural selection. If this process is real, our universe is part of a magnificent, endless cycle of cosmic creation. It's a chain reaction on the grandest possible scale. Our Big Bang could have resulted from a black hole in a previous parent universe. Over billions of years, our universe expanded, cooled, and formed galaxies, stars, and planets. Many massive stars have already collapsed and formed black holes, each potentially sparking new baby universes. This cycle would continue indefinitely. Baby universes born from our black holes would expand and mature, forming their own stars and galaxies. If their physics are suitable, their massive stars would also collapse. It paints the multiverse not as a static collection of parallel worlds, but as a dynamic, evolving ecosystem where universes are constantly being born, living out their cosmic lives, and giving birth to the next generation. This gives the universe a purpose, to create conditions for black hole formation, ensuring the cosmic chain continues. It's a beautiful, self-sustaining loop, echoing the cycles of life and death we see in nature on Earth. This cycle provides a potential explanation for time's arrow. Perhaps time flows in one direction because our universe was born from a black hole, a one-way process that set the clock for an entire cosmos. Let's zoom out and imagine what this multiverse would look like. It would be a colossal, ever-growing family tree. At the top might be some initial universe, or perhaps the tree extends infinitely into the past. This ancestor gave birth to offspring through its black holes. Each inherited slightly different physical laws. Some would be fitter than others, better at producing black holes. These fitter universes would have many more children, passing on successful traits. Other universes with less favorable physics would be evolutionary dead ends, sterile branches that never reproduce. Over eons, the multiverse would become populated predominantly by descendants of the most fertile universes. The branches belonging to successful lineages would grow and spread. This evolutionary pressure would naturally lead to universes like ours. We live in a finely tuned cosmos because it's the product of cosmic evolution. inheriting successful genes from a long line of fertile ancestors. This makes testable predictions. If we could tweak any fundamental constants, the theory predicts fewer black holes would result, not more. Physicists are actively exploring these possibilities, turning wild ideas into verifiable science. Smolin's idea is powerful and elegant, but it's not the only game in town. It competes with other profound ideas. One major alternative is the anthropic principle, which approaches the puzzle from a completely different angle. It starts with an undeniable fact. We are here. We exist, we are conscious, and we can observe the universe. This fact might be the key to the entire mystery. The weak anthropic principle is essentially a selection effect. We shouldn't be surprised to find ourselves in a universe with laws that allow life. If the universe were different, we simply wouldn't be here to wonder about it. Of all possible universes in a grander multiverse, we could only find ourselves in one of the rare ones, with the right conditions for conscious observers to evolve and ask these big questions. This idea is intellectually tidy, but for many scientists, it feels unsatisfying. It explains fine-tuning by saying it had to be this way for us to be here, but doesn't explain the underlying mechanism. Smolin's theory proposes a physical mechanism, black hole reproduction, that actively creates fine-tuned universes, offering a more direct evolutionary explanation than philosophical observation. Another major contender comes from cutting-edge theoretical physics, string theory. This isn't just a theory of particles, it's an ambitious attempt to be a theory of everything, uniting Einstein's gravity with quantum mechanics. String theory proposes that fundamental building blocks aren't point-like particles, but tiny vibrating one-dimensional strings. Different vibrations give rise to all particles we see, like guitar strings producing different musical notes. For string theory's mathematics to work, it requires extra dimensions beyond the three we experience. These dimensions are curled up into tiny, complex shapes, too small for us to see directly. There isn't just one way for these extra dimensions to be curled up. Physicists calculate there could be as many as 10 to the power of 500 possible configurations, a number so vast it's hard to comprehend. Each configuration would result in a different universe with unique physical laws. This collection is known as the string theory landscape. Our universe would be just one valley in this immense landscape of possibilities. This provides another explanation for fine-tuning. If there are 10 to the 500 possible universes, it's no longer surprising that at least one would have the right properties for stars, galaxies, and life. We just happen to live in a lucky one. This idea shares similarity with the anthropic principle, vast multiverse, and selection effect. However, unlike cosmological natural selection, the string theory landscape doesn't propose reproduction or evolution mechanisms. It presents a static picture of all possible universes existing simultaneously. Smolin's theory offers a dynamic alternative, where universes are born and selected over time, providing causal explanation for our particular cosmic location. Now let's venture into what might be the most mind-bending idea of all, the simulation hypothesis. This theory asks a startling question. What if our entire universe, including ourselves, is a sophisticated computer simulation? It sounds like pure science fiction, but it's an idea that some serious philosophers and scientists are contemplating. The argument assumes technological civilizations can develop computing power immense enough to simulate entire universes. If such civilizations could run ancestor simulations, they would likely run billions of them. For every one base reality universe, there could be countless simulated universes. Statistically, we'd be more likely to live in a simulation. In this scenario, the laws of physics aren't fundamental properties of independent reality. Instead, they're simply the rules of the program, underlying code written by simulators to govern how our universe functions. This provides a different answer to fine-tuning. Our universe has laws allowing complexity in life because that's what the simulators programmed. Perhaps they were interested in seeing how life evolves. The fine-tuning isn't cosmic evolution or lucky accident. It's deliberate, intelligent design by entities in higher reality. It's the ultimate creator hypothesis, but with programmers instead of gods. However, this is almost impossible to test. So let's pause and really let this sink in. What if it's true? What if Lee Smolin's incredible idea of cosmological natural selection is actually how the cosmos works? it would fundamentally change everything we think we know about our place in existence. Our Big Bang would no longer be the ultimate beginning. Instead, it would just be one event in an unimaginably long chain of cosmic births, stretching back through countless generations of universes. This idea would instantly reframe our relationship with the cosmos. We often feel isolated, a tiny outpost in a vast, indifferent void. But if this theory is correct, we are not isolated at all. We are part of an immense and ancient cosmic family. Our universe is a child of a previous universe, and it is a parent to countless others. This connects us to a lineage far grander than we ever conceived. This would also mean we're living inside a successful experiment. Our universe's particular physical laws are not a fluke. It's the product of cosmic evolution, a testament to rules that have proven incredibly effective at creating more universes. We are inhabitants of a fitter universe, one whose cosmic DNA has been passed down through generations because of its fertility. We are beneficiaries of a long line of successful universes. This changes our view of ourselves as well. As conscious beings capable of understanding this, we become the universe's way of knowing its own story. We are the children of a child of a child of a universe. We're looking back and piecing together our cosmic ancestry. The stardust in our bodies was forged in stars that could become black holes, potential seeds of new realities, connecting our existence to the birth of entire new cosmoses. If universes reproduce through black holes, it gives the cosmos a sense of direction and maybe even a form of purpose. Without this idea, the universe is often seen as a random, undirected process heading toward cold, empty darkness. But cosmological natural selection writes a completely different story. It suggests the universe is not just running down, it is also building up. It's constantly planting the seeds for new beginnings. In this new picture, the purpose of the universe would actually be to create black holes. The entire grand cosmic drama, galaxy formation, stellar birth and death, element creation, could be seen as necessary steps in a cosmic reproductive strategy. The universe evolves complexity not as a random side effect, but because complexity is the pathway to creating massive stars that allow it to have offspring. The universe is a machine for making more universes. This would change our perspective on fundamental laws of nature. We currently see constants like gravity as arbitrary numbers, but they are not arbitrary at all. They are the genes of our universe, honed by eons of cosmic evolution. Physics becomes the study of an optimized system, like a biologist studying an animal perfected by evolution. This gives new motivation to physicists. Every measurement deciphers the genetic code of a successful cosmos. Perhaps the most exciting consequence of this theory is that it might not be just philosophical. It could be actual, testable science. If our universe was born from a big bounce inside a black hole, it might not have been perfectly smooth. The violent transition from collapsing singularity to expanding Big Bang could have left subtle marks or scars on our cosmos. These would be tiny imperfections imprinted from its birth, clues to its dramatic origin story. Scientists are actively looking for such evidence. One place to search is in the cosmic microwave background, the faint afterglow of our Big Bang, a snapshot when the universe was just 380,000 years old. If our universe was born in a bounce, theories predict unique gravitational waves would have left a faint, specific twisting pattern in the CMB light. Finding this signal would be monumental evidence that our Big Bang was a rebound. Another way to test the theory is studying black holes themselves. Smolin's theory predicts our universe should be very good at making black holes, but not necessarily perfect. Evolution produces results that are good enough, not flawless. Physicists can create hypothetical universes with different physics and ask, would this make more black holes than ours? The search is on for these cosmic scars and deeper understanding of black hole formation. If we find this evidence, it would be the single greatest scientific discovery in human history, confirming that we are part of an endless, evolving, and truly magnificent cosmic ecosystem. The answer might be hidden in faint light from the dawn of time, or in complex physics governing stellar death. This discovery would reveal our place in an infinite, dynamic, and awe-inspiring cosmic family. We began this journey with a simple yet profound question. What if black holes make universes? We've traveled from the familiar night sky to the very edge of reality itself, the singularity at the heart of a black hole. We've explored how these cosmic monsters warp space-time, how they're born from spectacular stellar deaths, and how they populate our universe in millions. They're not just points of destruction, but profound mysteries signaling new physics awaits discovery. We delved into Lee Smolin's radical idea of cosmological natural selection. This theory paints a cosmos that is constantly evolving, reproducing, and improving. It suggests black holes are not tombs, but wombs, giving birth to new baby universes. This process, unfolding over countless generations, would naturally select for universes best at making black holes. It provides a stunningly elegant explanation for why our universe seems so perfectly fine-tuned for complexity. This idea transforms our place in the cosmos. We are no longer lonely inhabitants of a random accident. Instead, we are part of a vast, interconnected cosmic family tree, descendants of a long line of successful universes. The Big Bang was not the absolute beginning, but merely our universe's birth from a parent that existed before. This imbues the cosmos with purpose and direction, where stellar life cycles are fundamental mechanisms of cosmic reproduction. We've seen this stands alongside other mind-bending concepts, like the anthropic principle, the string theory landscape with its near-infinite possible universes, and the truly wild possibility of the simulation hypothesis. But what makes Smolin's theory so compelling is that it's not just philosophy, it's potentially testable science. It challenges us to look for scars of our universe's birth and study whether our reality is truly optimized for black hole creation. So where does this leave us? We stand at a thrilling moment in the history of science. We have built telescopes that can see to the edge of the observable universe, and detectors that can feel space-time ripples from colliding black holes. We are armed with theories that are both audacious and increasingly testable. The question of whether black holes create universes is no longer confined to science fiction. It's a serious scientific hypothesis guiding real research. The answer may well be within our grasp in the coming decades. The search for that answer is one of the greatest adventures of the human intellect, requiring us to combine knowledge of the largest structures with understanding of quantum scales. It's a quest that forces us to be humble, to admit the limits of our current theories, and to be bold enough to imagine new and radical possibilities. This journey of discovery is not just for scientists in their labs. It is for everyone who has ever looked up at the stars and wondered about the big questions. Where did all this come from? Why is it the way it is? Are we alone? The quest to understand if black holes make universes is part of this fundamental human drive to comprehend our origins and place in the grand scheme. It feeds our curiosity and expands our perspective. It reminds us that reality might be far stranger, larger, and more magnificent than we have ever dared to imagine. The universe is telling a story, and we are slowly, patiently learning how to read it. So the next time you see a picture of a galaxy or read about discovering a new black hole, remember the possibility we have explored today. You might be looking at the seed of a brand new cosmos, a cosmic parent about to give birth. The journey to know for sure is ongoing, and it is one of the most exciting stories in all of science. The mysteries of the universe are deep, but the human spirit of inquiry is deeper still. Keep asking questions, stay curious, and never stop wondering about the true nature of our incredible and possibly infinite cosmic home.